You may start now.
Greetings and good evening from India. Welcome to the second session of day 7 of IVWGST 2021. In this session, we have Professor Jure Žalohar from University of Ljubljana, Slovenia, as a keynote speaker. Thank you, Jure, for kindly accepting our invitation. Today's session will be shared by Professor J.R. Kyle, former Deputy Director General of Geological Survey of India. May I request my colleague, Dr. Chinmoy Rajkor, to proceed with today's agenda. Over to Dr. Chinmoy.
Thank you, sir. A very good evening to all. On behalf of IVWGST Organizing Committee, I welcome you all to this 14th lecture of this workshop. It is my pleasure to inform you all that today is the 80th Foundation Day of CSIR, that is Council of Scientific and Industrial Research. Our CSIR NIST, that is Northeast Institute of Science and Technology, the host institute, is among the 38 laboratories under CSIR. So coming back to this workshop, today we had a very delightful morning session. Morning session by Professor J.R. Kyle, sir, who delivered his talk on the seismotectonics of recent earthquakes in Northeast India, where he emphasized on the precursor appraisal. And now in this session, we have with us Dr. Jure Žalohar from University of Ljubljana, Slovenia, who will deliver his talk on a very new and interesting topic on the omega theory and the time-dependent earthquake forecasting. But before we proceed, I may request our session chairman, Professor J. Kyle, sir, for his initial remarks. Over to Kyle, sir, please.
Thank you so much. Very hearty welcome to Professor Žalohar on this very auspicious day of, Foundation Day of CSIR Labs. So we are looking forward to your very, very new topic to us on earthquake forecasting. So we eagerly wait to listen to you without any wasting of time. I just again warmly welcome you for kindly accepting our humble invitation. And this is a very good day for all of us. On the Foundation Day, you are giving this lecture. So thank you so much. Thank you. Over to Shantanu, please.
Thank you, sir. So now I will read out the concise biodata of our today's speaker, Dr. Žalohar. Dr. Žalohar is a physicist and geologist. He is a co-founder and co-owner of Quantictune AZ, a Swiss-based company dedicated to advanced earthquake forecasting. He obtained his PhD from University of Ljubljana in 2008. His main research fields are physics of faults and earthquakes, seismology, stratigraphy, and paleontology. Among Dr. Žalohar's most important achievements are a series of articles on a coherent mechanics of faulting for the Journal of Structural Geology and development of Tecto software for fault slip data and earthquake analysis, which is now recognized and used by structural geologists around the world. During numerous field trips observing tectonic structures in Alps, he and his colleagues made important paleontological discoveries, including identifying the oldest and only known fossils of seahorses, pipe horses, and pygmy pipe horses, new fossil sites with complete skeleton of Triassic reptilians, fishes, and other biota from the Tethys Ocean. His most important contributions to science is the discovery of a new physical theory of earthquakes that brings a redefinition and a solution to the earthquake prediction problem. In the last few years, he developed and tested the Quantictune earthquake forecasting system, which allow for time-dependent earthquake forecast and prediction based on the omega theory. It is an honor that IVWGST 2021 features a person of his stature. May I request Dr. Žalohar to enlighten us with his lecture. over to Dr. Žalohar. Sir, please continue.
Thank you very much. I hope you hear me well. First, I would like to thank you for inviting me and giving me opportunity to present you the Quantictune project. The title of this presentation will be the Omega Theory and the Time-Dependent Earthquake Forecasting. As you presented in the presentation, I'm a physicist with a PhD in geology. I work as a researcher at University in Ljubljana, Slovenia, and I'm also development director of Quantictune. So first, let me explain what Quantictune is. Who are we? Quantictune AG is a Swiss research company dedicated to advance the global earthquake forecasting and prediction. We are both a research institute and operational service. Quantictune has built the first operational earthquake forecasting system based on the Omega theory. The system also incorporates earthquake forecasting based on the lithosphere-atmosphere-ionosphere coupling, LIAC, which you probably know. In the future, also other approaches such as ETAS and B-value oscillations will be included. Our main offices are positioned in Ljubljana, Slovenia, in this building, World Trade Center in Ljubljana. We are currently building the control room, which will look something like this. This actually is not a photo from our offices because we have currently workers doing this, but the control room will be designed in the same way. So here we will create the first operational earthquake prediction and forecasting center. Our system is based on the so-called Omega theory. Everyone who works in the field of seismology, especially that part, which is connected to the earthquake forecasting, everyone knows that there is a lot of statistics, but very little physics. And it is clear to everyone that physics is missing in this approach in mainstream seismology. So now we know what is that missing physics. It is the Kusura Continuum theory or so-called Omega theory. The name Omega was chosen because all rotations in this theory are denoted by the letter omega. So it's a new kind of physics. It's very complex, mathematically difficult to understand. Among physicists, it's well-known fact that Kusura Continuum theory operates with very difficult mathematical apparatus, which is in complexity, can be compared to the general relativity theory or quantum mechanics. So it is almost impossible to go into details. Therefore, we will only discuss and mention some basic concepts of the Omega theory. So what is the Kusura Continuum? Bode's law, Omega sequences, chaotic synchronizations, tectonic waves in the Earth's crust. And then at the end, we will talk about Quantictune earthquake forecasting system, basic structure, results, and statistical tests. So what is the Kusura Continuum? The basic postulate of the Kusura approach is that the Earth's crust, which contains a large number of faults, can be modeled as a Kusura Continuum where blocks of rocks between the fault planes can rotate. So we have several fault planes in the rocks and blocks between these fault planes can rotate. In the Kusura Continuum, the description of deformation is based on the deformation gradient tensor U. Then we have torsion curvature tensor, and we have several rotational tensors like macro rotation tensor, also micro rotation tensor, and relative micro rotation tensor, which describe rotations of the blocks and also regions in large scale. So the corresponding stress measures are stress tensor sigma and couple stress tensor mu. As you see, there is not just a stress tensor in the Earth's crust, but following Kusura approach, we also have a couple stress tensor. Another important physical measure is the so-called Kusura characteristic length, L, which describes the size of rotating blocks. So now we should present the basic ideas of reactivation of the folds, or so-called Amotonsis law of friction. In the classical Cauchy continuum, the fold is reactivated when shear stress tau is larger than frictional resistance for sliding, which is defined by the coefficient of friction and normal stress. So when this tau becomes higher than frictional resistance, then it is supposed that an earthquake happens and the fault is reactivated. In the Kusura continuum, we add two additional terms, S and N. S is so-called shear traction and N is so-called normal traction. So actually on the fault plane, we have shear stress and shear traction, and then we have normal traction and normal stress. As you see from these equations, the characteristic lengths are in the denominators of these terms here. So whenever two characteristic lengths, Li and Lj, are equal, that will cause these terms to diverge, and the shear traction or the normal traction will become infinite. These are so-called rotational singularities. When shear traction is infinite, this will cause sudden burst of forces and energy without warning, which is equal to earthquake. So as you see, the Kusura continuum approach brings a complete redefinition of what is earthquake. In classical continuum, we thought that earthquake is produced by shear stress, but Kusura continuum theory shows that this view is wrong. Earthquake is related to rotational singularities. So this is very new, and luckily the process is predictable. Now we will talk about the Bot's law, which is the first important concept of the omega theory. It appears that in the Kusura continuum, faults cannot slip independently. As soon as slip happens along one fault, it will soon followed by slip along other faults inside some kind of cascade triggering. So faults interact, and we have several types of interactions. This type here is so-called parallel faults interaction, and this type here is so-called intersecting faults interactions, where this block slips along intersection line. We have some equations which describe these processes. This equation is called the equation of the parallel faults interaction, and is important for our presentation. This is example of parallel faults interaction in some mountain in Slovenia. As you see, sub-parallel faults and blocks which rotated between these fault planes. This process also occurs on larger scales. This is Slovenia, and we have several sub-parallel dynamic faults with north-west, southeast directions. The solution of the equation of the parallel faults interaction is based on the Rebound model, which is well known in seismology. But here we present the extension, the Kusura extension of this model, which is based, which incorporates at least two parallel faults. In initial state, the rock is undeformed, and then during the interseismic slip, the deformation increases. After earthquakes, this block between the rocks, between the fault planes, rotates back toward the initial state. So you see here rotations play a major role. The solution of the equation of the parallel fault interactions is very interesting. After some very complicated analysis, we derive these results, which show that two interacting fault planes or faults do not need to be of equal length or equal size. They can actually be of different sizes. And this ratio between the characteristic length of the first and the second fault is equal to the ratio of the recurrence time on the first fault and on the second fault, or reactivation times are also called these times. So these ratios are equal to B, which is the material parameter. In the same way as we have shear modules, Young modules, and so on, in the Kusura continuum, in the rocks, we have additional material parameter, which is called B. It is actually called Bode's parameter, because if we translate this equation into the language of the magnitudes, then we get this famous Bode's law, which in this shape is known since the work of Marcus Bode. And for long it was unknown what is this 1.2. The Bode's law describes the difference in magnitude between the main shock and the largest aftershock. And there were many studies in the past claiming that this actually is only the consequence of statistical scaling laws such as Gutenberg-Ritter's law and Omori's law. Actually, the omega theory shows that Bode's law has a clear physical basis, and this is related to the fault interactions. The important result is also this equation here, which shows that the reactivation time is linearly proportional to the size of the fault or rotating blocks. Now we come to the next important concept, which are omega sequences. So the interacting fault planes are not of equal sizes. Each next interacting fault is either b times smaller or b times larger, which creates such cascades of interacting fault planes. And then it is assumed that seismic activity migrates in the direction perpendicular to the fault planes, in this direction or in this direction. These are actually geometric cascades, geometric series of faults. Can such geometric series be found in nature? The answer is yes, and the most beautiful observations are in the mid-ocean ridges. This is example from the mid-Atlantic ridge system. If we take this part here, these yellow lines are transform faults, the red lines are ridge segments, and if we measure carefully this length, then we discover that actually this is geometric progression of transform faults. These black lines represents theoretically perfect geometric series, and these red lines represent the position of these ridge segments. So actually we have very accurate geometric series, and many such series exist in the mid-ocean ridges. So now we can take this relationship between the time, recurrence time, and the size of the faults, which is geometric, and we can translate this into the language of time and magnitudes of the earthquakes. So we plot the x-axis like that, which is time, y-axis like that, magnitude, and the corresponding magnitudes of the earthquakes follow this red curve, where the difference between the magnitudes is constant. This curve is logarithmic curve, and the theory predicts existence of such geometric successions of earthquakes along parallel faults. We call such geometric successions of earthquakes the omega sequences. So the omega sequences are equivalent of the repeating earthquake sequences, which are well known in seismology, but on larger scale. We have two different types, basic types of omega sequences. These are sequences, decreasing seismicity rate sequence, which happens in this way. And then we have increasing seismicity rate sequence, which happens in this way. Can we observe omega sequences in nature? Can we prove their existence? Of course, the answer is yes. First, we check on the mid-Atlantic ridge system because the geometry is so beautiful. And in this time period, for example, in 2014, for magnitudes above 5, we observed such beautiful, very well developed omega sequence. These black lines are theoretically perfect geometric series, and red columns are real earthquakes. As you see, this succession is very accurate and far from random. We can observe geometric omega sequences everywhere, not only on the mid-ocean ridges. This is some case study in Serbia, 2010 Kraljevo earthquake. Very well developed omega sequence everywhere. And this is another case study in northern Italy, Slovenia. If you take some part of seismic catalog, which seems random, actually we can prove it's not random. It is composed of multiplicity of omega sequences. These red columns are perfect geometric sequences. And as you see, there are many such sequences. It is very surprising that also on the global scale, large earthquakes form omega sequences, which point to large and long-range global earthquake interactions and rotations of tectonic plates. We also observe that these global omega sequences show surprising geometrical order. For example, this is one geometric sequence, and 3 of these earthquakes, number 2, 3, and 4, are positioned on approximately the same latitude, and the number 2 and 3 are positioned on the southern hemisphere. The number 4 is positioned on the northern hemisphere. So several geometrical rules were actually discovered. So what should you remember? Seismic catalogs are not random, but are composed of multiplicity of omega sequences. Now we come to the next important concept, which is chaotic synchronizations and earthquake forecasting. The idea is the following. If we find some omega sequence in the seismic catalog, we can easily extrapolate to calculate the next hypothetical event, like this. And if we do that for all omega sequences in the seismic catalog, then what we can do is to count the number of extrapolated events, this n. And this allows us to calculate so-called local interaction potential, which is a measure of instability of tectonic faults. So this is case study for Emilia 2012 earthquake. If we take this part of seismic catalog here, if we calculate the number of extrapolated events, we get such spike. And this spike almost perfectly corresponds to the main shock Emilia 2012 earthquake, which means that this approach can be used to forecast earthquakes. We conclude that numerous omega sequences synchronize the rhythm. Often they produce their next event approximately at the same moment. These are so-called time synchronizations or phase synchronizations. And this process actually is not new in physics. It's well known. For example, if you look at this video, we have several metronomes. We will start them randomly. Then after some time, they will start to oscillate with the same rhythm. So this is the process that it also is happening in the Earth's crust. I can show you 2 more examples. The Zagreb earthquake, 2020. If you take this part of seismic catalog before the Zagreb main shock, and then the computer extrapolates all omega sequences, then the Zagreb main shock almost perfectly corresponds to the maximum of the maximum density of the extrapolated events. Again, another example, Utah Salt Lake City earthquake in March 2020. If you take this part of seismic catalog after some slightly larger earthquake, or this one, and before the main shock, again the earthquake almost perfectly corresponds to the maximum of the extrapolated density of events. So these actually are manual analysis and can be used to forecast earthquakes. We come to the next important concept, which are tectonic waves. If we perform careful mathematical analysis of these omega sequences, as I told you before, it is expected that seismicity migrates from one parallel fault to next parallel faults, and the mathematics show that the velocity stays the same. It is some kind of a wave which travels in the direction perpendicular to the fault planes. We call this tectonic wave, and the theory suggests that such waves trigger omega sequences, and within one omega sequence, the time difference between the earthquake and the distance in the direction of waves is linearly proportional. So this is the wave which travels toward the right, and these are earthquakes within the omega sequence. The time difference and distances between the epicenters are linearly proportional. This is according to the theory. Can we find this effect in nature? Yes, indeed we can find it if we search it, and it's everywhere. This is only one example from Slovenia. These 4 earthquakes represent almost perfect geometric series, and also the distance between the epicenters in this direction of green vector n, which is the migration director, the distances are linearly proportional to the time differences. And as predicted by the theory, the observations is in accordance with the theory. The velocity or the direction of the wave is perpendicular to the major faults in this region. The velocity is small, 80 meters per day. So these are really slow waves. Our system calculates and analyzes thousands of waves each day, and it appears that most waves are emitted in the direction perpendicular to the major tectonic plate boundaries, like this example in Japan, for example, and in California. We have most waves emitted perpendicular to the Sant Andreas fault, for example. And surprisingly, everywhere on Earth, we observe another major direction of waves, north-south direction. And we assume that rotation of the Earth has some important role in formation of these waves. We know that these waves can be described by Singh-Gordon equation, which is a wave equation with additional sinus term here. This phi is actually the rotation of the blocks, and these waves then look some kind of a domino waves. The Singh-Gordon equation, the solutions of the Singh-Gordon equations are so-called solitons or solitary waves, like breeders' kink waves and anti-kink waves. They look like this. So here you see how these waves travel. Okay, now can tectonic waves be observed in nature? How to prove the existence of tectonic waves? First, time-distance relations between the earthquakes in the omega sequences prove the existence of tectonic waves. But there are 2 additional options. One is direct observation of deformation and stresses. I will present you later this. And also migration of seismic activity with a wave. If such waves really do exist, they could trigger earthquakes in different tectonic zones. And all these earthquakes should then be positioned on such circular lines. We expect to see this effect if such waves actually do exist. And of course they do exist. I will show you several examples. Now we will talk about Quantictune earthquake forecasting system. This system is very large, very complex. It contains several modules. I will only present you 3 of them. The first is so-called stress forecasting module, which uses moment tensor summation method by Kostro and Molnar, and the Kusura extension, which was described last year. And with this extension, we calculate a global tectonic stress field of the Earth. And these colors here show you tectonic shear stress field. Blue color is low shear stress, red and black colors are high shear stress fields. And then these small lines are maximum horizontal compressions. So these fields slowly change through time. From month to month, we can observe some changes in the global tectonic stress field. We also observe that major earthquakes and magnitude 7.5 plus earthquakes are linked to these dark regions. So this is first important information where we can expect really large earthquakes. Here is one example, observation of the breeder in South America during the years 2017 and 19. In this part, Chile, we observed slow oscillations of shear stress field, which almost perfectly corresponds to the breeders. So these stress changes prove the validity of the Singh-Gordon equation and changes of stresses which are caused by this process. Additional important observation is the new law for earthquakes, which is so-called maximum magnitude law. We observed that maximum magnitudes of earthquakes are defined by the normalized shear stress field, which is normalized in such way that we divide all values with the maximum value reached anywhere on Earth. So we see that maximum magnitudes follow this logarithmic curve, which is defined by this equation, and then this blue curve corresponds to the normal stress on the fault planes, which blocks the faults. So the largest earthquakes, the largest magnitudes are observed here in the field approximately around 0.6 or 0.8. And based on the Gutenberg-Richter's law, we can then calculate the expected rate of events globally. And we get this green curve. This histogram then shows observations of real earthquakes. So actually what we see is amazing result where the observations really well correspond to the theoretical prediction. This is example of the Tohoku earthquake. A few months before the event, the Japan was under moderate shear stress, and then suddenly this shear stress increased, leading to the major earthquake. So you see these changes of stresses were precursory. The second module of Quantictune forecasting system is time synchronization module, which calculates the local time synchronizations and local interaction potential in all tectonic zones worldwide with resolution of 1 degree. We use ensemble approach with 50 ensemble members. So what we see here is that actually tectonic plate boundaries are quite unstable, and this is very important. Although they are quite unstable, we clearly observe high oscillations of instabilities. This is one case for Alaska magnitude 8.2 earthquake few months ago, and here we observed high instabilities in this region. For example, in the epicentral region, the timing of the earthquake was clearly defined by such huge oscillations of the local interaction potential. And we also see in other earthquakes that they're linked to huge oscillations of the local interaction potential. What we also see is this formation of the critical regions. So this chart shows you the shear traction field. I will explain later what this is, but what is important here are these black dots. These black dots are highly unstable tectonic faults. If these dots are dispersed like this, the situation is not critical, but if they tend to cluster and form such clusters of black pixels, then this corresponds to formation of the critical region. And we observe that large earthquakes are linked to this formation of critical regions, where large regions are highly unstable, not just small dispersed parts of the faults, but large regions become highly unstable. This is example of Japan magnitude 6.8 earthquake in May 2021. The third module is ensemble forecasting module, which uses kink and anti-kink waves, single wave, this equation, and colliding waves like this equation, to calculate the shear traction which is produced by coupled stresses in the Earth's crust. So we produce such charts on a daily basis, and such charts show shear traction on the plate tectonic boundaries. Red color corresponds to high shear traction, and blue color corresponds to low shear traction. And you see clearly waves with such blue shadows. And what we expect is earthquakes happening in this red or near these red clouds. We calculate such forecasts for 2 months ahead, and it can be done for 1 year, covering each day. What we also observe is the maximum magnitude law for shear traction. We observe that maximum magnitude is linked to the increasing shear traction by this equation, by this logarithmic equation. And then in high values of shear traction, also we observe the effect of normal traction which blocks the faults. And the maximum rates of triggered earthquakes are again here near the value of 0.6 or 0.7. This changes slightly through time. Based on this fact, based on this equation, it is possible to formulate clear probabilistic models for earthquake triggering. We define the so-called global interaction potential PG, and then the probability for earthquake triggering on unstable faults is the product between the global interaction potential and local interaction potential. So the PG describes the effect of tectonic waves, and PL describes the effect of time synchronizations. And if we choose some point on Earth like this here, we observe very large fluctuations of shear traction field. Dot here is 1 day. So you see this changes from day to day. And this also changes considerably the earthquake triggering probability. Now I will show you 2 examples how this look. This is forecast and comparison with real earthquakes for Japan earthquake in May. As you see, this changes all the time, and large field produces increased rate of events, and also some major earthquakes with certain amount of probability. And this actually is an amazing forecast. Next case is for California. A few days ago, actually, as you see again, this shows changes of shear traction field, and these dots are magnitude 2+ earthquakes. If we compare this to the forecast, the real distribution of earthquakes, so first we have increase of shear traction here in the Gulf of California, which is linked to significant increase of rates of events, and then also the shear traction increases in this region here, leading again to some moderate earthquakes. So this changes all the time, and these actually are operational earthquake forecasts. Now, if you go further, we can add, or we can define even more complex models by introducing critical probability, critical regions for large earthquakes. The following conditions should be fulfilled simultaneously for large earthquakes. So first, faults should be in a highly unstable state. Then, second, time synchronizations. High instabilities must be present in a wider area, which means critical regions. Then strong tectonic waves with large characteristic length should produce very high shear traction. This is example for this Japan magnitude 6.8 earthquake. All aspects, all 3 points have been fulfilled. We had high unstable state, also critical region, and large or high shear traction field. And this triggered a large earthquake. Then we have the so-called rate model, which means rates according to the time synchronization effect. And the idea is that increased shear traction actually increases the expected rates of events. This is the average rate, and this is the then time-dependent rate. If we introduce critical regions, then it appears that rates for magnitude 7.5 plus earthquakes, for example, can reach values as high as rates for magnitude 4.5 plus earthquakes, which means that during, for example, next 14 days, we can get somewhere on Earth probabilities for magnitude 7.5 earthquakes as high as 90%, which is amazing. Then we use standard approach. We calculate the expected number of events, and then some Poissonian model, which gives us the probabilities for having an earthquake within some region during some time interval. And this picture shows you the last Nicaragua 6.5 earthquakes here, which corresponded to such huge fluctuation of the expected rates of events. So here are also other case studies for large earthquakes. These large earthquakes are always associated with some strong tectonic waves, producing strange and significant oscillations of shear traction field. So you see, always we have such high shear traction field. We also observe the effect that we expected. If such tectonic waves do exist, they should trigger several earthquakes all around the world. And this is one case study from the Mid-Atlantic system, where one wave in short time period triggered several moderate earthquakes. So this actually proves, this is the second proof for existence of tectonic waves. And this is another case study, amazing example of several earthquakes triggered by one strong tectonic waves in April 2020. Each day we observe thousands of such cases. Now we will present statistical evaluation of Quantictune earthquake forecasting system. The following questions should be answered. So how to perform the statistical tests, which parameters should be tested, and of course tests should be clear and simple. What we want to test is a relationship between the earthquakes and shear traction field. We make a hypothesis that real earthquakes happen during an elevated shear traction field. Random earthquakes on average do not follow this relationship. And possible tests which are included and automatically performed in the system are weak, strong tests, then score test of the wave activity, Morchan error diagram tests, and area skill score. This is the effect, this is the relationship that we want to test. The forecast for the Canese Islands in Greece, magnitude 7 earthquake in October last year. So this line is the forecasted shear traction field, and the actual event was actually perfectly forecasted. So the weak test statistically analyzed the average shear traction field during earthquake for magnitude 4.5 plus real and random earthquakes. In weak test, random earthquakes have an even distribution along the tectonic plate boundaries. And what we observe is that real earthquakes occur in approximately 10% stronger shear traction fields than random earthquakes. So this line is for real earthquakes. The average shear traction field for real earthquakes is higher than for random earthquakes. Interpretation is the following. The shear traction field is not considerably elevated in all regions along the tectonic plate boundaries. The next strong test, here we test the following: time-dependent forecast and average forecast versus real earthquakes and random earthquakes. Strong tests, in this strong test, random earthquakes mimic the real distribution of earthquakes on Earth, which means that these are time randomized catalogs. And the average forecasts are defined by simple average of the daily forecasts. What we observe is this line is the average shear traction at the time of real earthquakes, and this is at the time of this is for the average forecast. This is for the time dependent model, which changes day to day, but this is for the average forecast. So we see that the time dependent model actually produces larger shear traction at the time of earthquakes than the average forecast, which proves the reliability of the model of the Quantictune earthquake forecasting system. And the best performance is for large magnitude 7.5 earthquakes. Then we performed called score test. In the omega theory, there exists a relationship between the Kusura characteristic length, which is wavelength, and the maximum possible magnitude of earthquakes. Some equation. In theory, most powerful waves are those with large characteristic lengths, and these waves can trigger high number of earthquakes, which means they have high score. Definition of the score: this is the number of earthquakes triggered by a common wave. So this wave actually has score equal to 7 because it triggered 7 earthquakes. The real earthquakes, the results for real earthquakes are like this. We observed that most seismically active waves are or have wavelengths 22 to 24,000 kilometers. And then the Motion error diagram tests and area skill scores. We compare the reference model, which is average forecast, which is time independent, of course, and actual model, which is time dependent. And the forecasting, first we have to define the forecasting area, which is around these plate tectonic boundaries. It is defined in such a way that we eliminate the spatial forecasting skill. And on the x-axis, then we plot the fraction of space-time occupied by alarms. So alarms are triggered in those points which have the shear traction above some threshold. And on the y-axis, then we count the miss rate, the number of or percentage of the missed earthquakes. And for unskilled forecasts, we expect a position close to this diagonal line, and you see the results for the average forecast with eliminated spatial forecasting skill. So the average forecast has no forecasting skill. If we add the time, the temporal component of the forecasts, then we produce a significant gain over the average forecast. And here the area skill score, which measures the effectiveness of this forecasting method, is close to 0.59, which is low. And here we observe a significant increase of area skill score. Another example for California region, for example, during September 2000 and August 2021 for magnitude 2+ events in this region. So here again, average forecast has no forecasting skills, time component of the forecast significantly increases the performance of the forecast. And if we allow also spatial forecasting skills, so spatial and temporal forecasting skills for Central America, California during the August and September for 4.5 plus events, we produce such Molchan diagrams with area skill score close to 1, which means that the Quantictune earthquake forecasting system is able to forecast earthquakes not just in space but also in time. And this is the last slide, the state of the Earth today in the last days. So what is happening on Earth today? This chart was actually calculated already in the beginning of August, and in these days we have very strong tectonic wave which triggered this Acapulco earthquake here at the beginning of September, and then later also here in California, Nicaragua. This wave is highly seismically active and passes also through the region of Chile and this part here, South America, where we expect some increase of rates of moderate events and also some possible strong events. Another highly active wave is here. This one triggers several moderate earthquakes in this region between New Zealand and Fiji. And then we have some interesting event here in North Aleutian Islands, Papua, Philippines, and so on. So, in summary, the omega theory introduces a significant paradigmatic shift in seismology. Faults interact according to Bode's law. Earthquakes catalogs are not random, but consist of multiplicity of omega sequences. Omega sequences synchronize the rhythm to produce a large event at the same time. These are so-called time synchronizations. Then changes of tectonic stress and couple stress fields propagate through the Earth's crust in the form of slow solitary waves, which are tectonic waves with velocity up to 6 kilometers per second. The most seismically active are very slow tectonic waves with velocities up to 100 kilometers per day. Time synchronizations and tectonic waves are used to calculate time-dependent earthquake probabilities. In general, earthquake triggering can be forecasted with large probability. The forecast can be calculated for 1 year ahead for each day. Currently, we do 64 days forecasts. One model cannot forecast all earthquakes because the information in the model is smaller than information in the nature. Therefore, ensemble approach is used to increase the information contained in the complete ensemble. Quantictune earthquake forecasting system is planned to be released in 2022. Multiple levels of accessibility are planned, and the number 10, operational earthquake forecasting and prediction, has been solved both theoretically with omega theory and practically with the Quantictune earthquake forecasting system. So where to find us, where to know more? You can read our internet site. You can follow us on Twitter. If you want to cooperate with us or more information, you can also contact me personally or our CIO, Dr. Marko Komac, who is also the president of European Federation of Geologists. So I would like to thank you for your attention.
Thank you, Jure, for your brilliant talk on the need theory on earthquake process. It was really interesting. You have rightfully and successfully incorporated the theory of physics and theory of statistics with a geological concept in this theory. Now, may I request our session chairman, Professor Jure, for his final comments. Over to Professor Jure, sir.
Yes, it's absolutely, congratulations, Professor Žalohar. It's really very, very fascinating and very new techniques, I think, for all of us. And your arguments, your logic, your physics, I think all very, very logical, and hope something about the earthquake forecasting is coming near future through you. That's what is my speculation or anticipation. I should not say that I have understood everything. Little of it I have tried to understand. I just just a query whether practically you could do the forecasting because forecasting of magnitude less than 4 or even less than 5 is not really very a practical implication to the society. 6 and above magnitude, if we can forecast with time, space, then I think it will be very much useful for the society. You might have explained that, but still I want to know again whether you have been able to forecast a devastating earthquake in the recent past with this technique, and what is that earthquake, and what was your time period to forecast that within 7 days or within a month an earthquake of magnitude 7 is coming in such and such place. Could you please give 1 or 2 examples that where your technique or your computer simulation has been able to do that? You have said that about that Japan earthquake and other things, but exactly what was the magnitude and what was your prediction or forecast for that?
Yeah. Okay. Thank you very much for this question, which is a very important one. First, the question: what is or what should be the earthquake forecast, and what should be an earthquake prediction? Because these are 2 different terms. With earthquake prediction, we actually mean, for example, some claim that during some certain time period, let me say next 2 weeks or next week, we will have a magnitude, let me say, 6.5 plus earthquake in some chosen region. This is prediction. But forecast is different than prediction. Here we define probabilities. We do not specifically define scenarios, because different scenarios are possible with different probabilities. And that means that claiming any scenario will eventually fail, because all scenarios are possible with certain probabilities. And this is a major difference between the prediction and forecast. What we do is forecast. So we do not claim that, for example, major earthquake will happen. Like I said before, we do not produce predictions. We produce forecasts which bring a range of possible scenarios. And based on these probabilities, several safety measures can be done, which are useful for society. So this is the difference between the forecast and prediction. This is what we do. Of course, we upgrade now this forecasting system based on the omega theory, which brings forecasts also with the lithosphere, atmosphere, ionosphere coupling that you probably know. We cooperate with Dr. Pulinitz because this allows then to see what is happening with the radon emissions and possible atmospheric anomalies in response to the increased shear traction. And together, these 2 models, these 2 theories can potentially bring us closer to defining a specific scenario for some region. Of course, this is here a lot of research is still needed, but I'm certain that we are on a good path. What regards your previous question, what about other large earthquakes? It's very difficult to show you everywhere on all these past examples, because it would take us a lot of time. But first, what I would like to show you here, there is always high shear traction during the earthquake, or slightly, how to say, the occurrence of large earthquakes is always associated with high shear traction. And we don't have large earthquake in weak shear traction field. So this is the parameter that we have to watch constantly: the number of waves passing through the region, the value of the shear traction field, and so on. Actually, statistical tests and also comparison between large earthquakes in the past were all very good. Actually, the system, as I showed you here, performs best for magnitude 7 and magnitude 7.5 plus earthquakes, which means that almost all large earthquakes were well forecasted. They were linked to significant increase of shear traction field.
Thank you so much, Jure. You have really introduced us in a new field, and we will be, in touch with you and our young scientists from the NIST or some, other earth science department. Will be definitely fascinated by your talk, and I think there is a huge scope of learning and doing research in this field. Thank you so much for enlightening us with the new field in earthquake forecast. Thank you so much.
Thank you very much.
Thank you.
Thank you, sir. Thank you. We have a special guest, Professor Muhammad Farooq from King Abdulaziz University, Saudi Arabia.
Yeah.
Over to Professor Farooq for your comments.
I would like to thank you for this important lecture. Actually, it is very new for us. Yeah, it is a new science actually. The omega theory is the first time I hear about. I am very surprised about this method. Also, there's the new terminology like the tectonic waves, and this is good science. This is new science for us. Also, I don't claim that I understand well the details of the mathematics here. So I want to read more about it. But I am looking forward to see a real forecasting or prediction in your field. We are very glad to hear about this method. I don't have question actually, but I need to read more about this new science. And until then, I can. But I predict you to be the first one to forecast earthquakes in our Earth. Well, thank you very much.
Thank you very much. Actually, what I would like to say, I would only like to comment this. We are now building the operational center where we will have a large control room. Many people employed there, which will constantly produce interpretations of the forecasts. And this will be much in the same way as you see on the television for the weather forecasts. So this will be released to the general public and professional seismologists and so on. So actually this this operational center will produce the first publicly available forecasts, what can happen in the future with analysis, what is happening and what did happen in past days.
Thank you, Jure. So can we take some questions from the attendees? You have time? Can we proceed for the questions? Hello, Jure? Hello?
Yeah, we can hear you.
Okay, over to Pasija for question and answer session.
Thank you, sir. Thank you, Dr. Žalohar, sir, for such a wonderful talk. For your assistance, now I am going to read out the questions from the participants. And the first question is, what is the difference between omega sequences and Poisson distribution?
Thank you very much for this question. Yeah, so this is major, we should say, change in thinking, because we are all used to think that earthquakes are random or more or less random or independent. Poissonian model assumes that earthquakes are independent of each other. Of course, there are some problems in the classical seismology with this approach, because it's well known that clustering of earthquakes of real earthquakes is much bigger than Poissonian model predicts. And now in the omega theory, we change this philosophy completely. Now we show that earthquakes are far from being independent. They are interconnected. They are produced by a process of interaction between the fault planes. So parallel faults tend to interact most, but also faults that are oblique to each other tend to interact each other. And what we observe is that along parallel faults, earthquakes are never random. They form this succession, this geometric and periodic omega sequences. And of course, because the fault systems in the Earth's crust are highly complex, we then get a mixture of these omega sequences in the seismic catalogs, which then look like some kind of a random process. But actually, seismic catalogs are composed of a multiplicity of omega sequences. And indeed, there are times when seismic catalogs are very chaotic, but omega sequences tend to synchronize the rhythm, and this concept of time synchronization then reduces the chaos within the catalogs, and this mechanism is responsible for triggering of large earthquakes. So Poissonian model is still used in the Quantictune forecasting system in some way, but actually is wrong.
Thank you, sir. The next question will be, what is the epistemic uncertainty in the result of omega theory, how it is modeled?
So how the omega theory is modeled?
Yes, sir.
Yeah, so this is the Quantictune forecasting system. One part which runs on the internal computers is by Tectonic, not the version of Tectonic that structural geologists are using, but another version which has so-called Omega Architect. This is a very complex computer software, and this software actually can calculate low resolution and high resolution, and also ultra high resolution forecasts for entire world. Yeah, the Tectonic runs in Delphi, but other parts of Quantictune system like GIS system, and also some software in the backend, this runs Python.
Thank you, sir. There are a lot of questions from the participants. The remaining questions we are going to email you. If you don't mind, sir, you can answer them via email. Thank you, sir.
Yeah,
over to Dr. Santanu, sir.
Of course, you can write me on the email, and we can answer that also. Sure, if you will be interested to know more about this Quantictune forecasting system, Quantictune constantly performs meetings and workshops for seismologists all over the world, providing more information, because the system is huge. Dozens of people are working on it, and it's difficult to explain everything in 1 hour.
Sure, sir.
Thank you. Thank you, Professor Jure. Now, may I request Mr. Navajyoti Molia for a vote of thanks. Or to Mr. Navajyoti Molia.
Thank you, sir. Namaskar. A very good evening to one and all from Assam, India. On the evening of 80th CSIR's Foundation Day, it's my proud privilege to propose the vote of thanks to all on behalf of the CSI NIST family and the entire organizing committee of IBWGSC 2021. Firstly, I convey my sincere gratitude and hearty thanks to Dr. Jure Žalohar of University of Ljubljana from Slovenia for readily accepting our invitation and delivering today's talk on the omega theory and the time-dependent earthquake forecasting. Thank you, Dr. Žalohar, for sharing your experience with us and enlightening us with significant information of this new theory. We are very fortunate to have you as one of the keynote speakers. I also express my sincere thanks and gratitude to Dr. G. Narahari Shastri Sir, Honorable Director of CSI NIST Žalohar, for providing moral support and abundant help in conducting IBWGST 2021. I place on record our deep sense of gratitude to International Advisor of this workshop, Professor Andy J. Michael of USGS, and Session Advisor, Professor Daping Zhao from Tohoku University, Japan, for their valuable suggestions, support, and encouragement throughout the event. Our heartfelt thanks go to the session chairperson, Professor Jaya Kail, former Deputy Director General of Geological Survey of India, and co-chairperson Dr. Saurav Barua, Chief Scientist of CSI NIST, for their immense support and guidance towards the event. I would also like to thank special guest of today's session, Professor Muhammad Farooq Abdul Wahed from King Abdul Aziz University, Saudi Arabia, for his gracious presence despite busy schedule. I also extend our deep sense of appreciation and gratitude to Dr. Shantanu Barua, the convener of this workshop, for conceptualizing such a stunning idea to organize this virtual workshop and thus facilitate the direct access of the geoscientific fraternity with the experts and pioneers in seismology and tectonics from across the globe. I warmly thank all the members of technical staffs and organizing committee for their dedication and timely support toward the online meet. Last but not the least, I would like to thank all the attendees for their active participation in today's event, without which this event would not have been a success. Further, I solicit your continued support during the course of this workshop, and I look forward to see you all for the next session, which will go live at 10 a.m. tomorrow. Our keynote speaker for tomorrow's session is Dr. B.M. Tiwari, Director of CSIR, National Geophysical Research Institute, India, with his lecture on lithospheric structure of Himalayan collision zone. With this, I conclude with hearty regards and anticipation. Namaskar, and thank you all for your kind presence. Dhanyavad. Thank you, sir.
Thank you, Professor Žalohar. It was very interesting.
Thank you. Bye.
Thank you. Bye-bye. Bye-bye. Take care.